So let's first recall what we did last time. So last time the story went like this. So if you have a Lie group, then you can consider its tangent space at identity that we denoted as G small. And on this tangent space at identity, we defined bilinear operation, which was called Lie bracket. It's defined canonically. We used chart to define it, but it does not. We proved that definition of this does not depend on chart. So it eats two elements of G and gives us another element of G. And well, we didn't spell it out last time, so let us define such G. So G tangent space to G capital with operation which with this binary operation Lie bracket is called tangent Lie algebra. And suppose that we have a linear map. So suppose that L, it is a linear map from one tangent space at identity for one group to another. So this is linear map between two tangent Lie algebras. Such that this linear map is consistent with bracket on G1 and with bracket on G2. Namely, if I take L of two elements x1 and x2 in G1 and bracket in G1. So I indicate it by putting 1 here. This will be bracket in the algebra G2, which I indicate by putting 2 in here. L of x1, L of x2. So if we have linear map such that this happens, then L is called homomorphism of tangent Lie algebras so one important example of homomorphism of tangent Lie algebras is a differential of homomorphism of Lie groups. And let us formulate it as a proposition. So suppose that I have phi, it's a map from G1 to G2, and it is homomorphism of Lie groups. Then d phi differential of phi at identity in G1. Well, sometimes when it's clear what identity I take, I don't indicate in notation identity of what group it is. So it is clear here that it is in G1, right? So this is a map from TE G1 to TE G2. And a statement is that it is homomorphism, of tangently algebras. Let's prove this. Okay, so in the same way as in here, we indicate by index 1 the Lie bracket in TEG1, by bracket with index 2, it's a bracket in here, right? So we need to prove this thing where instead of L I have DE phi, right? So let me fix two centered charts around identity, one for G1 and another for G2. So let psi1, psi2 be centered charts around, so the charts of what? Of G1 and G2 respectively. Centered means that psi1 of E and psi1 of E is 0. Well, it is 0 as a vector, right? So vector 0. And psi2 of E is also 0. We can choose such charts. And let me now define, so the computation will be will be similar to what we had when we proved that such thing did not depend on chart. So let's see, we need to define the following linear operator, which is actually, you can think of as a metric. So you, in the corresponding coordinates, all corresponding to psi1 and psi2. So this is C, and well, it is differential of the following map. You apply psi1 inverse, then you apply phi, right? Well, this phi, right? Psi1 inverse goes from Km to some, well, to a neighborhood of identity in G2. Then I can apply phi, well, of G1, then I apply phi, right? And then I apply psi2, which goes from this neighborhood of identity in G2 to Kn, where n is the dimension of G2, right? Okay, and so of course we would like these charts to be, well, all the neighborhoods that I'm talking about are small enough such that all this composition makes sense. It always can be done. Then I'm using definition of the quadratic form that I needed. So first of all, I have. So let me take phi of x and phi of y, and consider its group commutator. So I remind you that if I have z and w, and this notation means it is, and these are elements of some group, Lie group, G. Then this means z w, z inverse, w inverse, right? So I'm taking two elements x and y in G1, map it to G2, consider as group commutator in G2, and also I would like to consider its coordinates, which I denote by double overline. So what it means? So if I consider some element x, so psi 1 of x, this is also notation from last class. It's x bar, and psi 2 of x of maybe some y, right? It is y double bar. So double bar means coordinates of an element in G2 with respect to the chart psi 2. So this is in G2, commutator, group commutator in G2, and we consider its coordinates as a function of coordinates of phi of x and phi of y. Well, it is, as we noticed last time, it is some bilinear quadratic form, which I will denote Q2, in terms of coordinates of phi of x and phi of y, plus, right? So this is like this. So plus terms of degree greater or equal than 3 in those phi of x double bar and phi of y double bar. Okay. Then I'm going to use this matrix C. It is chosen in such a way that actually I can rewrite phi of x double bar as a function. So this gives me coefficient in the for the linear term in expansion of this thing is a function in x bar. So this is C x bar plus plus terms of degree greater or equal than 2 in x bar. C is exactly this C here. Very well. And so I use this, right, and apply it to this guy. So I will have phi of x, commutator with phi of y, double bar. It is C times, well, you see now I'm using that the fact that phi is a homomorphism of groups. So therefore phi of x y, right, is phi of x phi of y. So this is group commutator of x and y in G1. This is group commutator of phi of x and phi of y in G2. And this is because phi is homomorphism of groups. So therefore, I'm using this, and apply it to and replace x here with commutator x and y. I get c times x, y bar, right? Plus terms of degree greater or equal than 2 in x, y bar. Okay, so then I'm using this, and I'm going to express this right, I'm going to express this in so right, so yes, this I'm going to express this as a function of x bar and y bar. So I'm continuing this, so I have phi of x, phi of y double bar. Now I'm using the fact that this thing is some bilinear form Q1 in terms of x bar and y bar, and all other terms in here, they are of degree greater or equal than 3 in x bar and y bar, and so therefore I should have here plus terms of degree greater or equal than 3 in x bar, y bar. Okay, this is one thing. On the other thing, okay, you see I started with some computation here using Q2, right? So let me denote this computation as star, and I can continue, so continuing star. I get that the same thing, phi of x, phi of y, double bar. So I have its Q2 of phi of x double bar, phi of y double bar, and then I apply to here, to each entry here, I apply again this formula. Okay, and so I will get it is Q2 of x bar, of cx bar, c y bar, right, plus actually terms of degree greater or equal than 3. And therefore we have the following conclusion. So they're just comparing this with this. We have that C Q1 of V1, V2 is the same as Q2 of CV1, CV2 for any V1 and V2 from Kn, where n is a dimension of G1 here. Okay, so we are going to use this. So let me see. I need to check. So my proposition is what? That d phi is homomorphism of tangently algebras. So it means what? It means that I would like to take differential, apply it to the bracket of two elements, xi and eta, and these elements belong to G1, right, where G1 is, so G1 is this space, tangently algebra, and G2 is this tangently algebra. And this bracket corresponds to G1, so we indicate it by this. Okay, so we need to now to just expand the definition of this thing, right? So the definition using the chart psi1. What was the definition? I need, so d phi. The definition was, so d e phi is left. Then we have definition d psi1 should be d psi1 inverse, right? Then q1 of d psi1 of xi, then d psi1 of eta. This was precisely the definition of this bracket. That doesn't depend on which psi1 we choose, but we chose this one. Right. Now I'm using this, right? So it means that what? Q1 of V1, V2 is C inverse Q2, CV1, CV2. So this equals to D psi1 inverse. Then instead of Q1, I get C inverse Q2. Then C D psi1 of xi, C d psi1 of eta. Now I need to remember what is my C, right? So C is actually d psi2, d phi, and then d psi1 inverse. So if I take inverse of that, so let's see what's going on here. A d psi1 inverse C inverse. If I take inverse of that, d psi1 goes to the left hand side, and then this inverse becomes just 1. And this cancels with this 1. And what is left is d phi inverse, right? And then d psi2 inverse. Okay, what is C times, and I multiply by d psi1 from the right. Again, it cancels with this one, and so I get that C d psi1 is actually d psi2 d phi. And so therefore, I can continue this calculation. So this equals to, this I replace with d phi. Sorry, I forgot that I have d phi still here from this one. So I have d phi. Then I have this, which is d phi inverse, d psi2 inverse. Then I have Q2 of C times d psi1 is d psi2 d phi of xi comma d psi 2 d phi of eta. Equals to, so this cancels, and this is exactly, by definition, bracket, second bracket of d phi of psi d phi of eta. And this is exactly what we needed to prove, that this equals to this. This is exactly the fact that d phi is homomorphism of tangently algebras. And so the proposition is proved. Okay, this is very important calculation. So now we know that if the differential, so to say, is a functor between the category of Lie groups and tangently algebras, loosely speaking, right? On this is some abstract fact, but also there's very important corollary of this. We can look at some very particular homomorphism of Lie groups. So suppose that I have Lie subgroup. H is a Lie subgroup of G. Right. Then I, which is an inclusion map from H to G, is Lie group homomorphism. Actually, it can be, H even can be virtually subgroup. We can go in even in this generality. And therefore, I can consider differential of I virtual, which is from tangently algebra H small of H to tangently algebra of G. And this is homomorphism of tangently algebras, according to what we proved. So therefore, and it means in particular that if I have bracket, if I take two elements, x and y, and these are elements of H, and I compute the bracket of H, then so di is just inclusion in here as well, right? So this means that actually this is the same as considering elements of x and y as elements in G and computing the bracket in G. So it means that, so it actually means that if I have Lie group, any Lie group G, which is a subgroup of, or even virtual subgroup of GLN, right? Then I know that corresponding Lie algebra G is a Lie subalgebra, then tangent Lie subalgebra in GL, in small GLN, right? Meaning, so when I say it's a Lie subalgebra, I exactly mean that, right? So the corresponding inclusion here, differential of this, gives me inclusion of G inside the Lie algebra of this, is just, which are just all n by n matrices, all of them, including zero determinant one. And corresponding bracket in G of two elements, x and y, is exactly should be computed like this. So I should think of x and y as an elements as n by n matrices by differential of this inclusion, and then I just compute commutator, because I know what is the Lie bracket here. We computed it last time. It's just commutator, and so this is just x and y in GLN, which is xy minus yx. So we know now Lie bracket, how to compute it for a lot of tangent Lie algebras. Okay, so our next goal is to prove a very, very important property of this bracket, which is called Jacobi identity. Proposition. So let G with a Lie bracket like this be a tangent Lie algebra. Then for any three elements x, y, z in G, we have we have what is called Jacobi identity. How to write it down? Usually I do it like this. So it is commutator of two commutator, right, and of first of two of elements, and then commutator of the third with commutator of the first two, and so I need to put them in cyclic order, take a sum, and this equals to 0. So namely, I put it like this, plus. So then I take all the cyclic permutation of this. So I can y goes to here, z goes to here, and x goes to here, plus I can squeeze it in here, I guess. So z goes in here, x goes in here, y goes in here, and this equals to 0. And this identity is called a Jacobi identity. Okay, so let's prove it. And on the way of proving this, we'll encounter a couple of very important notions, namely what's called adjoint representations of Lie algebra and adjoint representation of Lie group. Okay, so what is the idea? We need to consider the following map, linear map. So just define define the following map. It's called, it is denoted as follows. Ad stands for adjoint homomorphism. We'll prove that this homomorphism, but for now we just define it as just a linear map. So it goes from G to GL of G. So G itself is a vector space, and we have Lie algebra. We have algebra of all linear transformations of G, right? And we can take commutator of this, and this will be a tangent Lie algebra of all linear transformations on this vector space G. This is what it is. So what is add then? So I take an element in X and map it to the transformation which taking a commutator with X. So I take an element in G, and a linear map gives me back another element which is X, break it with this element that you chose in G, right? So this is definition, and goal is to prove that that add is a homomorphism of tangent Lie algebras. But if we prove this, then we prove a theorem, like a proposition. So because so suppose that I take right, so I take an element X, I take a bracket X with Y, and I would like to see what add makes with it. Well, obviously by definition, it is then, it is mapped by add to X, Y with some, so to this linear transformation, right? On the other hand, if I know that that add is homomorphism of tangent Lie algebras, it would mean that this thing is the same, right? Well, maybe I should write equality sign here and add of X, Y. Right, so add of, so this is then add of X, and then Lie bracket already in here, so add Y. So this would exactly mean that add is a homomorphism of tangent Lie algebras. But what is this thing? So it is, what is the bracket here? We know that the bracket here is actually just commutator. So it is just add X, add Y minus add Y, add X. Then we just open this up using the definition of add, and we get. So it means that first I apply add y, right? It is transformation like this, and then I apply to the result add x. So I take bracket with x minus, and for this term I have what? First I take add with x, so dot with x, and then I apply add y, so I get this. And I know that this equals to this, right? If I prove that add is a homomorphism of algebras. But this is exactly this, so equality sign in here. This equals to this is exactly Jacobi identity. I just need to put z instead of dot. I get this part gives me x, y, z equals to, here I have x, and then y, z, bracket goes to here, minus y, x, z. That's what I get. Now I just need to use that x, y is minus yx for any y and x. This is because the group commutator of two elements of the group G1 and G2 right? Again, I remind you that this is G1, G2, G1 inverse, G2 inverse. So if I replace two things, if I replace G2 and G1, as I did here, right, but for tangent spaces, then I get inverse. Well, this is easy check, and from this, since taking inverse in the group corresponding on the tangent space to take a negative sign, of course, all of this is loosely speaking. You should prove it rigorously, but there is no surprises here, right? So taking inverse corresponds to taking minus sign on a tangent, the algebra level case. We have this, and I'm going to use it. And so this, I would like to realize that this is the same as this. So what can I do? Well, x, y, z is already in here, right? So x, y, z I keep on the left. Maybe, so since I have to move, I would like to move this to this. No, okay. So this I'm moving to the right hand side. So let's see. Right, so on the left I will keep 0. This I move to the right. When I move it to the right, I get minus sign, and I kill this minus sign just interchanging this z with this bracket, and I get z with x, y. Plus this term, which is already as we needed over there, x, y, z. And instead of this minus, right? I would like to put plus and interchange this z index. So I get y zx, which is the middle term there. So this is exactly the Jacobi identity. Okay, so now we need to focus on proving that add is homomorphism of tangential algebras. So how to do that? We would like to see that it is actually differential of homomorphism of corresponding Lie groups. And what is this homomorphism of Lie groups that we need? So first, let us consider this map, which is just conjugation by an element G of our Lie group G. So this is a map from G to G, and it works like this. So it eats H and gives me G, H, G inverse, and this is G that we fix in the beginning and stays in this subscript in this map. Then I can consider a differential of this map at identity. This will be the map from the tangential algebra to the tangential algebra. Right? And this map is actually so then I would like to consider map which I denote also as add by first add is capital. First A is capital, and it is also stands for adjoint representation or homomorphism, but for group, not for algebra, and this is why this A is capital. And so this is map from G to G, L, G. So all invertible linear transformations of this vector space. And it is given like this. So I take an element in here, and the result of this add is D, E, C, G. So this is an invertible linear transformation from G to G. And it is invertible because, well, I can take G inverse here, and DECG inverse is the inverse of this map, DECG. So this is invertible linear transformation in here. And I would like to show two things. So claim. First is that add is homomorphism of Lie groups. Homomorphism of Lie groups. And second, differential of add is exactly this map add small that we introduced a few minutes ago. Then we'll be done, right? Because if we prove that it's homomorphism and add small is differential of add capital, this would mean that add small is homomorphism of Lie tangential algebras, and by what we showed here is hence we prove Jacobi identity. So this is our claim. Let's prove it. So to prove one, we need, so proof. First of all, it's clear that at capital is homomorphism of groups. Not homomorphism of Lie groups, but it just preserves multiplication structure. So let me introduce the following notation. So at G, right, is by definition, it stands for D, E, C, G. So it's actually image of G under this map. Rather than writing at of G in parentheses, I would like to reserve this notation because this is map itself, and I can still write something in parentheses here, meaning that this element would act on something in G small. So that's why this goes to index. Similarly, so here, of course, we used this parenthesis here. So I would like to switch actually to the following, that at this parenthesis, I would like to move to the subscript at x, and I would like to apply it to y, and this would mean just x, y, the bracket of x and y. So this is just some notation that we are going to keep throughout the course. So to prove, to see that at is just a homomorphism of groups is easy. Just need to understand what is at G1 times G2. Well, it is D, E, C, G1 composed with D, E, C, G2. Then we used the property of differential to say that this is, ahead of going. So this is not this one, right? But rather at G1 composed with at G2, right? And then it is differential, the density of CG1, CG2, while conjugation is action of group, so therefore it's D, E of CG1, G2, and this is by definition at G1, G2. So therefore, at is group homomorphism. We just need to see that it is smooth. So to see that it is smooth, we would like to prove the following lemma. So suppose that F, it is homomorphism of groups, as we have in our case. So this is homomorphism of groups. And G1 and G2 are actually Lie groups. But this is not yet homomorphism of Lie groups, just a homomorphism of groups. So Lie group, Lie groups. Then F is smooth if and only if its restriction to some neighborhood of identity is smooth. So this is neighborhood of identity. the proof is pretty elementary because, so what can we do? So proof of lemma. We just need to notice that, well, if I denote F1, well, just smoothness is local condition, right? So the thing is that we have the smoothness around high density, and we would like to smoothness around any point, right? So we just use the fact that it is homomorphism to move F to any other point in G1, right? And well, we have, let's denote F1 as F restricted to neighborhood of identity. F2 is F restricted to some neighborhood of some element G, right? Then, so this is neighborhood of some G in G. Then I can write the following, that F2 is a function, well, it's actually, U of G is not some neighborhood, but we would like to take, just to prove smoothness around the point. It doesn't really matter which one we take. We can just take UE and move it by G. Okay. Then what we can write? We can write that F2 as a function is expressed through F1 as follows. It is composition of three functions. Okay, shift by G inverse, then F1, and then shift by F of G. So this is from G1 to G1, this is from G1 to G2, and this is from G2 to G2. Why is this true? Because, well, F right of some point G tilde, which is in U of G, right? So this is because F of G, F of G inverse G tilde, right? So I take first multiply by G inverse from the left, I get to UE, then I apply F1, which is the restriction of F, to UE, then I multiply by F of G from the left, and then I go, then I get exactly a restriction of F on UG, which is F2. And here I just use the fact that F is homomorphism, right? Because then I can, you know, kind of factor this F out, and G inverse will cancel, and then I'll get this. But all three of these functions are smooth. Well, so this smooth, these are just diffeomorphisms. So therefore F1 and F2 are smooth simultaneously. And so therefore the lemma is proved. Which means, and so what we need? We need to prove the smoothness of Et. We know already it's group homomorphism, therefore for by lemma it's enough. So by lemma it's enough to check smoothness of at just one point. So let's pick this point to be identity. So at E. Okay, to do this, well, there's no. So we'll unfortunately just do it explicitly using coordinates, but this is not as bad as you might think. So let's see. We need to consider the following map, alpha. So this map is from two copies of G, from the direct product of G to G. This is a smooth map, which is actually an action. So this is an action of conjugation. So you take a pair of points. Here this is really a pair. Do not confuse it with the group commutator that we introduced earlier. So, and it is mapped to G, H, G inverse. This is really an action by conjugation, Lie group action on G on itself. So let me take some coordinates. So these are coordinates on G around identity. Well, they are centered, so such that x1 of E, x2 of E, xn of E is 0. So let me consider. Let me just consider another copy of the same coordinates. Just denote them by different letter y's to indicate that this copy belongs to the second copy of G here. So x1, xn is the coordinates in G, and then let me take another copy of the same coordinates and make them coordinates on the other factor. So these are coordinates of G times G, right? And this is another copy of coordinates x1, xn. Okay, and so we would like to work in these coordinates. All right, and so we would like to take this map and consider its coordinates, right? So, and denote them as follows. So, ith coordinate of this map of, and this depends on two coordinates of G and H, which are x1, xn, and y1, yn. Right? So this is ith coordinate of alpha of G, H, right? Such that, well, actually this I can put it here. This is of G and this is of H. These are all the notations so far. But let's see what's going on. Then we can take CG. What was CG? CG, what I fixed G and consider, so CG is really this map when G is just a fixed point and H varies. So we have the following. So we have CG, right? It is a map from G to G, such, and this is really alpha restricted to just one point fixed in the first factor and everything else in the second factor, right? So this means that CG in coordinates looks like this. It takes coordinates of H, which are y1, yn, and gives me back bunch of n other numbers, depending complex or real, depending on my field, which are fi of x1 of g dot 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 xn of g, then y1 dot 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 yn. And these are, so these are fi, si runs from 1 to n, right? So n numbers here goes to n numbers here. And this is how CG works in coordinates around identity. Then consider differential of G. What should we take? So this is actually then n by n matrix which is explicitly given as follows. I just have to take coordinates, Jacobian, so to say. Well, Jacobian is determinant, right? Well, matrix of the Jacobian of the map F with respect to variables y. So I should take dfi of x1 of g dot 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 xn of g, and then y1 yn. Should take differential of this with respect to dyg, and this will be, and then take differential at what? At y equals to 0, all y's, yi. And well, this is some number depending on g, actually. And this number depending on g, I and j. So and this is matrix whose ijth entry is this one, right? And it depends on coordinates of g somehow. So this matrix is exactly n by matrix corresponding to DECG in coordinates x1, xn. So this is explicitly what's going on. And we need smoothness of each entry of this matrix. But because F is smooth, it depends smoothly on these entries, its derivative depends smoothly on these entries, and x depends smoothly on g because these are smooth coordinates around identity at g. So therefore, it's evident here that well, we have, and well, just by definition of at in coordinates, it's just like this. We take it's right at, right, it is g, right, and gives me DCG, which is in coordinates is this matrix DCG, right? So in coordinates on G, it eats coordinates on this element G, so x1, so xn, and brings me dfi of x1, xn, y1, yn, derivative with respect to yj at y equals to 0. And we see that this depends smoothly on x. So at is a smooth round identity. So therefore, это smooth. So therefore, it is homomorphism of Lie groups. And this is just part one of our claim. So our part one in our program was to prove that it is homomorphism of Lie groups. And second is that differential corresponds to small et. Okay, so let's prove part two. Okay, so to prove part two, we should look at this. So we should take differential of et again and look at it explicitly. So we take differential of et. It means that I actually, so here we took differential with respect to y. Since et and coordinates like this, taking differential is taking derivative with respect to x now. So what I'm talking about concretely looks like this. So d et is in chosen coordinates is, well, so it is, so d et, right? Et was from G to GL, okay, et was from, just a reminder, right? From G to GL G, and d et, it is from Lie algebra of G to linear transformations of G as a vector space. So therefore, so this is n-dimensional vector space. This is n-squared dimensional vector space. So this is n square by n matrix should be. Right, this is a reminder. Just to justify that it's n squared by n. And which looks like this. So I take et. So first index, it is so d et. First index, which is like a double index corresponding to this n squared. And then second index is single index corresponding to this n is exactly, so I should take this and take x1 blah 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 xn, y1 yn. I take derivative with respect to yj, and then take derivative with respect to xk, so this k. So this is when y, then put y equals to 0, then x equals to 0. So this is just unveiling all the definitions of a derivation of a map in coordinates. That's exactly what we're doing. Okay, so this formula we need. Now let's see. So fi, let us go back to our notations. So if I consider fi of gh and consider it in coordinates, right? What we would like to denote by this line. So it is exactly So what it is, it's G, H, G inverse bar. But G inverse is exactly group commutator of G and H times, so group commutator would be G inverse, H inverse. So I need to kill one H on the right. And I will have bar here. But this is in coordinates, it's just sum of the coordinate of group commutator and coordinate of H plus degree plus terms of degree greater or equal than 2 in GH bar and H bar. Then I can continue because I had the notation, so I can continue in the following manner. So this equals to Q of G bar H bar, right, plus H bar. Q is quadratic form, right, which is bilinear. When it comes out of the group commutator, when I expand it as a Taylor series in G bar and H bar, and also I would like to, I will have terms of degree greater or equal than 3, right, in G bar and H bar. All right. This is very important observation, because what is going on here? So I take in second derivative of fi, right, with respect to y and x. So actually I can I can write Q of two vectors x and y. It looks like as follows. Sum explicitly this quadratic form of the following kind: xy, yj. And this is a vector actually, right? Well, let me put I in here, k here, and index I in here. So therefore, and sum over k and j here. Then comparing to this formula, so I take fi, right, and coordinates of g and h, which are x1, xi's and yj's. So I take derivative with respect to y and derivative with respect to x, put y equals 0, x equals 0. So what I get, what survives? Only something that comes out of Q. Everything else will give 0 out of this after this operation. And then the result will be that add d add ijk. So sorry, here I have kj also. This depends on k and j. So these are some numbers. So numbers. which are called structure constants. Then dA at ijk is exactly C, these numbers, C, I, K, J. Just going through, so the second derivative, so I differentiate with respect to y, I get this, with respect to x, put 0, get this, and so this exactly these numbers that I get after differentiating 2 times. On the other hand, let us go back to the definition of bracket. So if I have this, right, this actually, looking at the definition of the bracket, means that if I take D, we have basis in the tangent algebra, right, corresponding to this coordinates that we chose, which is d over dx i's, right? And in just following the definition, which uses q and some coordinates, we have that bracket of d over dxk right? And we look at this as an element of tangent space at identity, right? At x equals 0, right? With d over dx j at x equals 0 is exactly sum over I from 1 to n d with coefficients c. So what we did, we took vectors, moved them to kn, which tangent space to kn itself, and plugged them into q, and considered this as a tangent vector again using this coordinate. So and this was the bracket. So I have to put, instead of x and y, yes. So this exactly means what I'm writing right now. So it is ckji d over dxi at x equals to 0. In other words, small at, it's another n by n squared by n matrix. It's ij, like double first coordinate, second coordinate, right? What was that? So actually, if I fix I, right, it's a map from G to G, which eats element d over dxj and gives me this sum, right? It means that as this matrix is its ijk element is exactly cikj. And so I compare this and this. And so I see then that differential of at, we just explicitly showed that in coordinates, these two things coincide. And this is the missing statement that we needed. So this thing is homomorphism of Lie groups. Differential, which is coincides with this, is homomorphism of Lie algebras, and this gives us Jacobi identity. Few more words, and then I'll finish. So all this study of tangent space at identity of tangential algebras motivates the following definition. A definition of an abstract Lie algebra. A definition. Abstract Lie algebra. So G is an abstract Lie algebra if, well, first of all, G is a vector space. Is vector space. And, well, together with bilinear map which is denoted as follows. This is a map from G times G to G, called Lie bracket, such that the following properties are satisfied. First of all, it is antisymmetric. So for any x and y and g. And second, this bracket satisfies Jacobi identity. So Jacobi identity holds for the Lie bracket. So you see, I never say that this vector space actually is finite dimensional. In principle, so of course, our motivating example was finite dimensional, so tangent space of some manifold, which is finite dimensional manifold. But in principle, abstract Lie algebra can be infinite dimensional. And well, in the second semester of this course, we'll actually study infinite dimensional algebras. But main examples of, for now, will be finite dimensional vector spaces G. Well, speaking of examples, well, first, and the motivating example is tangent Lie algebras. Okay, so, well, another example would be if I have, so suppose that I have, so let A be an associative algebra. Then A is a Lie algebra such that bracket is given by commutator. So bracket is just AB minus BA for any A and B from A. Another example is, very important example is derivations of an associative algebra. So suppose that I have again associative algebra. Then derivations of A. So these are all linear transformations, right, of A such that they satisfy Leibniz rule. DAB, well, A and B are elements of A. It's associative algebra, so therefore I can multiply elements, right? So this is the same as DAB plus AD of B. Then, actually, if you have two derivations, it means that then it can be checked, just a simple exercise, that the commutator of D1 and D2, right, which is commutator in usual sense, so D1 D2 minus D2 D1 easily break it. Well, first of all, it is inside, it is also derivation. And this is the main thing. So once it's a derivation, then derivations are closed under taking commutators in GA, and therefore, and this is, of course, it is anti-symmetric, satisfies Jacobi identity, and therefore it's a bracket. So this is another example of abstract algebra. Well, just to give some example where bracket is not a commutator, so consider maybe R3 with a cross product. You can check that this is Lie algebra. The cross product gives you satisfies Jacobi identity and symmetric, of course. So this is Lie algebra. This is actually isomorphic to the tangent Lie algebra U2. It's not, which is not, well, it's easy, but not like just immediately obvious. Which is isomorphic also to tangent Lie algebra of SL3. So SU2 is a simply connected cover of SL3. So their tangent Lie algebras actually isomorphic. But we will get to that in the future. And actually, well, a big secret, which is like a big theorem rather, is that it says all the Lie brackets are commutators, because all Lie algebras are subalgebras of GLN for some big enough n. This is only for finite dimensional Lie algebras. So this is called adjoint theorem, which will not be proved, but well, it's a very important fundamental theorem.